Welcome to Advanced Data Analysis 2 with me, Erik Erhardt, Professor of Statistics at the University of New Mexico. In this video, we will be discussing Worksheet 25, covering chapters 16 and 17 for both discrimination and classification. So I'm scrolling down to this assignment and opening that up. We are revisiting the San Juan River Razorback suckers dataset provided by a previous student. And the initial part of this summarizes the data set. We've got the Razorback suckers that were collected in 2014. We've collected 4 elements. Each of them has 1 to 3 isotopes. And we've got, in this case, 4 known sources and 1 unknown source. And our goal here is to use the observations that of the known sources, create either a linear or quadratic discriminant analysis function to perform classification. We're going to assess that classifier using the jackknife or leave one out cross-validation. And once we're happy with the classifier that we've developed, then we're going to predict which of these 4 sources do the unknown fish belong to. All right, so there's a lot of data, or excuse me, there's a lot of code in this assignment, but there's very little for you to actually change. And I'll point out the specific places where that happens. Okay, a lot of this code up front is a repeat of class 23. So we read the data set in. The full data set has 1,500 observations. We remove the missing values to get down to 1,450. And we factor the source variable. We log transform the barium measurements to sort of spread them out a little bit more. And so that we have our source and 9 isotope variables. All right, here's a key place of difference. We're going to make predictions of the unknown fish using the known fish. So we need to partition the data sets. So we're going to take the original data set and filter to keep only the source unknown fish and put them into their own data frame with an underscore unknown. Then we're going to overwrite the original data set by keeping all the sources that are not unknown, so the 4 known sources. We're going to do a little more cleaning. We have a couple small CA values that we're going to remove, so we're going to keep anything that's above 0.5, and then we're going to refactor the sources to remove the unused unknown factor level. All right, so for our unknown fish, we have about 650, and for our known fish, we have about 800. So now we're ready to go. Let's look at our known fish. Now here's a huge scatter plot. You might include a select statement here to select just one of the isotopes for each element. But we're just looking at this to make sure that we're sort of happy with our starting point for our known data. You can see the high correlation between the elements, between the isotopes of the same element. But there's some unusual purple points right here. But I would say this is a pretty good data set to start with. I don't recommend. Please don't change the data set. I want everyone to have the same data. All right, classification. So here's our goal. We want to develop a classification using discriminant analysis that will reliably classify new observations from the known populations. Once we're happy with that, then we'll apply that classification model to the unknown population. And hopefully we'll be able to determine which source each of those unknown fish came from. All right, so this next set of plots, I'm going to actually scroll down below, has to do with the model assumptions. So state the assumptions of both LDA and QDA, the linear discriminant analysis and the quadratic discriminant analysis, and then interpret the plots above to evaluate whether we met the assumptions. So two things here. There's an assumption about LDA that is not made in the QDA, okay? And that has to do with the second set of plots, right? So these are, I've basically visualized correlation matrices because it's really hard to look at all the numbers, right? The assumption for LDA, I don't care if I tell you, is that all the covariance matrices are equal. And the QDA is exactly the same model, except it relaxes the assumption of equal covariance matrices. So effectively, if we look at those four plots, do they look the same to you? So blue is a positive correlation, red is negative correlation, and what I'm seeing are some differences, particularly in the barium, calcium, strontium corner. SJR seems to have some positive correlation here, whereas this one has negative correlation. This one also has negative correlation. This one has positive. This one has some strong negative correlation in this block, but this is sort of weakly positive or almost zero in NAP. So to me, it looks like there might be some differences here that are systematic between the groups. That may be enough evidence for me to not go with LDA but choose QDA instead. What's the other assumption up here? Let me zoom in on one of these. So these are, right, so we're accustomed to looking at QQ plots, quantile versus quantile plots for checking normality. Really hard to do when you've got multiple dimensions. So there is a way of assessing the normality based on Mahalanobis distance. So I've got and those Mahalanobis distances should follow a chi-square distribution if the data are multivariate normal. So these points should follow the red line in that case. I would say that a couple of these look pretty good, actually. The top right looks great. The bottom left looks great. The top left and the bottom right don't look that great. It's not that many points, 2, 4, 6, 8, 10, 12. Same thing over here, but there's definitely some deviations there of multivariate normality. Now, there are ways of assessing or addressing that issue. You could be looking into transforming the data, see if you can improve the normality. Now, a transformation that fixes the normality for SJR may actually break normality for the other groups. So you may be doing a tug of war that you can't win by doing transformations. What I recommend is not changing the data, but simply state what your conclusions are about these model assumptions, and then go forward and do the analysis even if the assumptions aren't met. All right, the next step is to do model selection to determine which variables you want to have in your model. Okay, so I have, by the way, so I've done all the analysis below using LDA, but you'll probably, if you decide to do QDA instead, just do a find and replace of LDA and replace it with QDA to get going. Use lowercase letters everywhere. We're going to do both backward selection and forward selection to see whether those models select the same variables, and yeah, okay. So what do we start with? We create a data set that just has the numeric variables in them, the data, and then we have another data set with just the sources. We need these separate groups for the way the functions work down below. So do set this random number seed. In fact, we'll just keep it at 7 so that everyone has the same result. We're going to use our step classification function within the KLAR package. here's the method, LDA. We're using backward selection. And we're going to save that result here. Step SJRS underscore B for backwards. All right, so we start off with all 9 variables. We drop 1. Okay, we drop SR 86 to get 8 variables. We drop 87 to get 7. And that took no time, basically. Well, it took 2 seconds. All right, this then is the formula from the backward selection. This formula is the resulting model. It's the which classes, what are the 4 sources, and these are the 7 remaining variables that we kept in the model. This result.pm is our correct rates and our error rates. So we expect, so within the training set, we have about 84% correct, accuracy. That's the main result there. Let's try forward selection. So we're going to start with an empty model. Make sure that you've got the correct LDA or QDA in there, and do forward selection. And by the way, this improvement, this is your stopping criterion. If I add a variable and it doesn't improve the classification accuracy more than 0.1%, then I'm not going to add that anymore, and I'm going to stop. Each variable I add needs to improve the classification accuracy by more than 0.1%. So here I start with 0 variables. I add in BA to have 1 variable, and then strontium, magnesium, strontium to have 4 variables total. It took 2 seconds to run. And these, in this formula, these are the variables I retained. And the accuracy here is about 83.7. Let me compare that. I'm going to jump up for a second. 83.7 for the backward. In fact, those to 7 decimal places, 837, 1044, 837, 1044, those are the same. So different variables, interestingly, but exactly the same error rate. So they're probably doing exactly the same prediction. That's sort of interesting. This is a visualization of the what the model selection did. For backward selection, we started off at whatever it was, 83% accuracy, and it decreased a tiny bit and then stopped. And for forward selection, we started at 0% accuracy, and then we grew basically up to 80% right away, and then it stopped after 4 variables were added. All right, so here is another place to do something. Are you going to use the result from the backward selection or the forward selection? From the accuracy that we just saw, it doesn't really seem to matter. So choose one of them. Make sure that you're using the appropriate LDA or QDA here to do the classification. And this is the final model that we're going to use. When we look at this final model, we have the prior probabilities for each group. That is basically what in our training data set of our known populations, what proportion of all those observations were from DEX, were from each of these 4 groups. Okay, so about a quarter were from these first 2 groups. There weren't as many from these NAPs, and there were about 30% from the San Juan River. Within each group, this is the multivariate mean, or sort of the center of their groups. Not much really to interpret there. These are the coefficients of the linear discriminants. Again, not much really to interpret there at the moment. And here's the things to write down. So discuss the differences between the backward and forward selection results. You can talk about how the sets of variables are different or the same, right? Do they include the same set of variables? How different are the accuracies for those 2 models? specify the final model. That's sort of what you did above, but indicate here in the solution what you chose. And then indicate the expected classification accuracy of the selected final model. So what you really probably should be doing is, we saw up here, after we did forward selection, for example, we did $result.pm, and that gave the accuracy rate of 83.7%. So what I would do is add this $result.pm. I'd copy this line so that you've got a second line for the result, LDA underscore SJRS underscore final $result.pm, so that you print this out for that final model. All right, sorry, I didn't mean to jump around so much. All right, and that will give you the accuracy. All right, next. So now we're going to look a little more closely at the accuracy by evaluating the confusion matrix for classification. Confusion matrix is the difference between what the true source membership is versus what the model predicted the membership to be. All right, so we're going to look at a table for this. So do make sure that you've specified correctly the either LDA or QDA. The rest of this you don't need to change. So this does the cross-validation of the known values. It puts those into this data frame here, and we also have these posterior probability predictions. Let's see, and I do some stuff and ultimately we're going to look at this confusion matrix right here to see how things were classified. So this here is the confusion matrix, and the way we read this is these columns are the true source labels, and these rows are what they were predicted to be. So of the DEX, in the DX column, 223 of them were predicted to be DEX, and one of them was predicted to be GJH. So not too bad to miss one out of 224. Basically, values along the diagonal are correctly classified, and anything on the off diagonal was incorrectly classified. You'll see for the second population, all of them were correctly classified. That's a dream. That almost never happens in real life. NAP, most of those were incorrectly classified as SJR. So we did a bad job with NAP. Only 18 of them were correctly classified. Okay, the overall accuracy was 83%. That could be pretty good. In a natural setting, I think that's pretty good. And we also have statistics by class. So within DEX, for example, there's a bunch of statistics here for different metrics about how the classification went. If we looked at the balanced accuracy at the bottom, almost 100% classification accuracy for these two groups. Only 55% accuracy for NAP, but 86% for the San Juan River. So we do pretty well for all three groups, or all four groups except for NAP. So did I already answer? Sometimes I do that. Determine whether some populations are better classified than others. Okay, talked about that. Or whether each population seems to have roughly the same error rate. Okay. Finally, we're going to classify the unknown observations. So now we'll use the final model that you selected to predict observations from the unknown population. So we're going to, for each of those 647 unknown fish, we're going to label them as being from one of the four known sources. So we're going to use that data from the unknown group we're going to make predictions using that unknown group. We're going to use the variables from that were used in the model that you selected, and we're going to use that final model to make those predictions. All right, then out of those predictions, I've got these posterior probabilities, which I label and so on, and those create determined classes. And finally, I'm going to bind all those observations together into a single data frame and plot them. And the plot is using two of the variables that are most discriminating, the barium and the strontium. I'm going to color it based on the true, either the true or the predicted class, or the predicted population or group. And I'm going to facet it by the source. Okay? And so from this plot, we want to, so let's just talk about the plot briefly. The facets are the 5 populations, DEX, GJH, NAP, and SJR, as well as the unknown. And they're colored by their classes. So red is DEX, green is etc., right? And really the only interesting thing here is the unknown group and how it compares to the other 4. So reds here are unknown fish that were classified as DEX. Green fish were classified as GJH, etc. So you might be wondering what the heck is happening here with the unknowns. I certainly am. So discuss the main features of the unknown population, right? What do you see here? What's happening? You may not be able to explain what's happening, but you can may not explain why it looks the way it is, but do explain what you see. Secondly, explain why you think the classification accuracy is expected to be either high or low, right? Do we think we're doing a good job classifying these unknown fish, or should we have any reason to doubt our classification accuracies? Okay. So we don't know what the true labels are for the unknown observations. That's what makes them unknown. But we're sort of just making a prediction. Do we think we're doing a good job? All right. I hope you have a good time with this assignment, and I hope this walkthrough has made it much easier.